Okay, welcome to the A/B testing replication crisis lightning lesson. And this is basically things we learned from 10 large-scale A/B tests. So I first want to start with a slide on who I am. I went to Stanford, got a PhD in machine learning. I was then director of data mining and personalization at Amazon. And one of my teams was WebLab, the Amazon experimentation system. This is where I got hooked into the field. I was at Microsoft for almost 15 years. I led the analysis and experimentation team. Fairly large scale. We were launching about 100 new treatments every workday near the end and continued to scale after I left. I think they're now at about 300 a day. Went to Airbnb, led the relevance personalization and the experimentation. I co-authored this Hippo book, which has been translated into all these languages if you prefer one of those. And I'm now consulting and teaching. Little housekeeping, the meeting is being recorded. I will post to LinkedIn the recording and the slides later today. So if you want the deck, there's some underlines linked that are useful. You'll be able to just go to that post and get them. Please feel free to ask questions. If they are relevant for the slides, I'll answer them live. If not, we'll try to answer them at the end. There'll be some time for Q&A. And I'm going to start with an amazing story. So back in 2010, there was a paper that was based on what today we think of as a tiny experiment, 42 people. And it reported that if you do a power pose, so put your hands high or do the Wonder Woman thing, you will have elevated testosterone, lower cortisol, you increase the tolerance for risk, and your feeling of power. So pretty amazing result. And then, the one of the authors, there was 3 authors, gave a beautiful TED Talk. It's a nice talk. I listened to it, but in hindsight, highly misleading, as I'll tell you. It goes viral. It becomes the second most viewed talk for multiple years. Tens of millions of people listen to it or view it. And then 5 years later, this was 2010, 2015, somebody says, hey, I'm trying to do a replication. It's larger than what you did. And it fails. And it fails on 3 out of the 4 outcomes. The only statistically significant outcome that does work is the feeling of power. So you tell people, make a pose to make you feel powerful. And people say, yes, I feel more powerful. This was called sort of a manipulation check. But the rest, sorry, did not replicate. Data Colada, a bunch of smart people that try to find sort of flaws and have done amazing work. They showed that the initial experiment was highly underpowered. It had about 6% power, whereas we recommend about 80%. So I'm not going to go into details about this, but power is the probability that there is a difference of some size that you will actually detect it in the experiment. And the standard recommendation is 80%. In 2016, there was enough articles, enough data, and the lead author wrote a note saying the evidence against the existence of power poses is undeniable. I do not believe that power pose effects are real. There's a law called Brandolini's law. It says the energy to debunk something far exceeds the energy to make the claim. And this is a good example of that because, in 2025, last year, when I look at the statistics, this talk, which is based on effects that fail to replicate, is still the 3rd most viewed talk. It has 75 million plays as of November. And in the last year, it was played 2.1 million times, over 5,700 every day. Listen to this talk, which is now known to be based on data that does not replicate. So science is supposed to be this self-correcting, process. It is slow and it is hard to correct stuff. And Some things I'm going to talk about today are like that. So let's first look at what happened in psychology. Pretty interesting area to learn from. We all know that sort of replication is the cornerstone of science. If you come up with a claim and other people are able to replicate it, you can gain trust in that claim. So in the 2010s, there was this realization that many of the published findings in psychology fail to replicate. I showed you the amazing story of power posing, but social priming, right? If you read Kahneman's, Nobel Prize winner wrote a book, Thinking Fast and Slow, summarized the field, and he has a whole chapter on social priming. And he says, you gotta believe it because the evidence is indisputable. Well, turns out the evidence was really weak. It was based on studies that were small, had low power, did not replicate. Ego depletion was a theory that held back for many years, appears in books, and then people said, hey, it doesn't replicate. And there's a nice article by Shimak who says, look, if all the results that you get are sort of borderline, then you must suffer from what's called the file drawer problem. Everybody else that isn't replicating, sticking into the file drawer. So we are basically getting a false positive here. Bem published a paper in 2011 called Feeling the Future, and he claimed that ESP, extrasensory perception, is real, and he was able to show it using commonly accepted statistical methods at the time. So the problem is if our standard toolbox for showing that something is stat sig shows that you can prove ESP, then there's a problem, right? Most people don't believe that time can flow backwards. So the question is, what else is wrong? And so, of course, when people tried to replicate this, it failed. And today we can see his stuff as p-hacked. That's why I said at the time, because today I think our standards have grown. This would not be a sufficient study by today's standard. Breakthrough research in 2015, a big collaboration project by the Open Science Foundation said, well, let's pick 100 studies and try to replicate them. Of these 100 studies, 97% were statistically significant. In the replications, only 36%. If you look at the effect size, it was about half. So here's a graph, from the paper where here's the original effect size and here's the replication effect size. So anything below the diagonal means the replication is weaker. And you can see that many of the results are below the diagonal. And anything that is sort of not bluish means it was not stat sig. So very, very influential paper, seminal at the time, showing, hey, we're publishing all this stuff and things do not replicate. Why? Well, low statistical power. People are using smaller samples than they should. And when power is low and you get a statistically significant result, you suffer from what's called the winner's curse. The winner's curse. The true effects have to be exaggerated. Okay, so let me say this again. If you're running with low power under 50%, then the true effects must be exaggerated for you to get a statistically significant result. P-hacking, there's this nice paper showing that a lot of researchers have too many degrees of freedom. They choose when to stop. They don't necessarily pre-declare the condition. They choose to remove outliers in ways that were not pre-declared. They look at subgroups. All these things are giving you a lot of false positives. The ability to get a statistically significant result when you should not have, given your size. Then there's publication bias. Journals love when somebody says, oh, we found this amazing result and the p-value is below 0.05, right? But if then somebody else submits a result that attempts to replicate it and it's not statistically significant, well, they tend to get rejected, goes into the file drawer, right? So what we see in journals is a highly skewed view of extreme results. What we don't see are all the failed replications, basically. And then another problem is called harking, hypothesizing after results are known. So you'll see experiments where, the the key outcome, what we call the OEC, overall evaluation criterion, A/B testing, was not pre-declared, and people run the experiment, and then they find some metric that moved, or they find some segments, and they publish the result, not disclosing that this was not pre-declared. JC asks, how much do you think this replication crisis is due to pressure to publish? Absolutely. Absolutely. I mean, there is huge motivation to publish to get your tenure at the university. And so, if you get a result that's borderline, if you can remove some outliers. Now, some things are not intentional. Like, people think that they're doing okay, right? Oh, we look at the data in detail and we see this outlier, and we just remove it, right? Or we remove outliers that are meeting some condition. But what you're not realizing is when they haven't pre-declared it, they're now effectively p-hacking. They're going to get more statistically significant results than they should. So I do think it's absolutely like that. And that's why the standards are now changing, right? Journals want you to say, hey, I pre-declared my result, or this is what I'm going to do. And there are sites and ways to do that. So here's the trigger for why we started this project that I'm going to talk to you about. There was a paper that was published, peer-reviewed, reasonably good journal, the Journal of Consumer Research. These three authors published a paper called Curvy Digital Marketing Designs, Virtual Elements with Rounded Shapes, Enhance Online Click-Through Rates. Okay, so the claim is, here's an example from the paper. This small website had square corners to this button, and then they made them round, right? And so the claim from the paper is that if you go to rounded shapes, you are going to enhance your online click-through rate. Okay, I'm going to refer to the paper as BAC for the three authors. And so the paper has multiple examples. Two of them are A/B tests. Okay, and when I refer to an A/B test, randomized, online, controlled experiment. Okay. Here's the two. One was Google Ads, had 65,000 impressions, so looks pretty reasonably sized, not too small, not the N equals 42. And so 65 and 83. And then it's kind of funny, they advertised their budget of, about $200 that they spent on this. So not even very expensive. They probably should have spent a little bit more and gotten more reliable results. But they report this massive lift to click-through rate, 25%. Mohammed asks, why is power the pertinent aspect here? If small sample sizes or weak effects is the culprit, wouldn't that be reflected in a large p-value? No. So again, I'm not going to go into details here, but if you're running an underpowered experiment, then let's say you run an experiment with 20% power, then 8 out of 10 times, you're not going to sort of see a statistically significant result. But the 2 out of the 10 times, that 20%, you are going to get a statistically significant result that suffers from the winner's curse. It will have a low p-value, and it will exaggerate. It must exaggerate if you're running with power under 50%. Okay. And again, I teach all this stuff in my class. We're not going to go into the details, but it is, people think that you only need the p-value. No, the p-value loses credibility if you're running in low power scenarios. It is true that most of the time you will not see a statistically significant effect. When you do, it will be exaggerated. That's very important. Okay. So second experiment, the homepage element. This is the example that is shown here in the visual. It's a little startup site. They had a square versus round corners. Look at the small numbers. 474 visits versus 445 visits. Massive lift, 55%. Okay, so if you look at the paper, when I read it, the first thing I noticed was, these numbers, the 65K and the 83K, that invalidates the experiment. Why? Because they were running it as if it was equal assignment, and this is clearly not equal. And in fact, you can do the test to show that there is a sample ratio mismatch. If you are trying to run a balanced experiment and you get an unbalanced number of users or number of visits, then you have a sample ratio mismatch. This is a red flag. It invalidates the experimental results. Something is wrong. Okay, so what went wrong? Well, we know that Google Ads, despite the name that they give the feature, they call it A/B test. It is not an A/B test in the sort of statistical definition of being randomized. They do not randomize. In fact, they tell you that they intentionally diverge the delivery to maximize the ad spend. They do what you want them to do, which is to find the best people who will click. But it's not a randomized controlled experiment. Okay, there's a nice paper that says, oh, we found 133 published studies that they all mistakenly claimed that this was a randomized controlled experiment. It is not. Okay, now somebody must have given them that clue, because in the paper the authors write the assignment of consumer to ads is not randomized. We acknowledge this shortcoming of the study. So I'm not sure whether they should have put the study at all, because they're effectively acknowledging that this is an invalid experiment. Okay, so that's one out of the two. What about the second one? So the second one has a 55% lift to click through. This seems, boy, extraordinarily large, right? If the true effect was really anywhere near this would have like wide-ranging implications for the whole industry, right? Everybody should stop what they're doing and change to rounded corners. Lucas Vermeer, Jacob Lanowski, and I have been intimately involved in lots of A/B tests by multiple companies that ran a lot of UX experiments, thousands of these. We have never seen anything that moves by this amount, especially not for UI changes like colors or shapes or things like that. So our experience is that lifts generate are typically less than 1%. Maybe you could say 3%, 55% unheard of. Let me see what questions. Nicola says, in the realm of online experiments, how much of this is replication crisis is also due to attempt to implement more complex stats as method as sequential. I do not think this is the problem. So if you design the experiment correctly and pre-declared that you're going to do sequential analysis or group sequential analysis, the stats work out. So I don't think it's the problem with the fact that we're using more fancy statistics. I think most of these are violations of the basic statistics, p-hacking, lack of power, things like that. So there's basically two principles that, guide our skepticism. Carl Sagan says extraordinary claims require extraordinary evidence, right? So if you're going to claim something extraordinary like 55%, you better have really good evidence. This was not there. It was very borderline. And then there's Twyman's law, which I love. Any figure that looks interesting or different is usually wrong. And boy, if I applied this, anytime somebody shows me an experiment that's like over, 10%, I'm like, okay, before we announce it, let's double and triple check it. It's likely to be a problem. So we started this project called the Trustworthy A/B Patterns. And it's an MVP version of minimum viable product. So we don't have the funding of the Open Science Foundation that gets a lot of contributions and donations. We said, we're just going to do it in a simple way. We'll give you free consulting. We'll help you design, we'll help you validate, we'll help you run, and we'll help you analyze the results of several patterns that we think are worth looking at, including this rounded corners, if you allow us to publish the results. Okay, and we're going to respect your sort of the crown jewels. You don't have to publish the absolute numbers. We'll just have to publish numbers like lift, which are relative. And what I'm showing you today are the results of the first 10 replications. Okay, so let's start with this pattern, right? The rounded corners that was published. There's now a paper that is out there that you can read. It has just been accepted recently, so you'll see it next month in the journal. But we brought in some heavyweight people because we knew there was going to be a lot of pushback. So Guido Imbens at Stanford University, Nobel Prize winner, is a co-author. Andrew Gelman, who published some of the seminal papers on power analysis, is a co-author. They helped us, write this correctly so that we can say, hey, the original result is incorrect. Okay, a hard message to get accepted. And then these are the partners that we worked with. So Joachim from Co-op, Ravi from SeaWorld, and Fabrice from the vendor Chameleon. So what was our process here? First of all, we said, let's gather some data and estimate what one would expect from such a UI change based on similar experiments. Okay, that allows us to define what's called the MDE, the minimum detectable effect, so that we can determine how many users we need for replication runs. So we calculate the sample size based on power analysis. This is what basically everybody should do. This was not done in the original paper. There's no power analysis. And then we want to run multiple experiments that have sufficient power. And then at the end, if our results show that, hey, the effect is much weaker, then we have to understand how we can make this claim stronger. And we use an approach called small telescope, which I'll describe to you. Really cool idea. So first of all, what are typical effect sizes for UI changes that are similar? So good UI is a nice repository. They have a couple of button experiments. You can see the effect, 1.8, 1.6, with 620,000 visits and 297,000 visits. So reasonably large numbers relative to, remember, this was 500 that were done in the experiment that was published. And these were not even statistically significant. So even these numbers aren't high enough. And then there's a repository called Evido. They have a nice practice, unique selling proposition, which is slightly as close as we can get. It had a large effect of 6.8%, and then some Apple Pay, which is close enough, 6.1, social buttons, 1.2. So you can see nothing in the realm of like 55%. We also point to a paper by Bing that says, hey, the average experiment 0.3% and Airbnb 0.3%. And then we did a poll. We asked people, and we picked only respondents who said they were running more than 10 A/B tests. And the estimated, this is the distribution of what we got. So some people did think this was going to be like an 8% win or a 5% win, but most people are around the zero. The estimated lift was 0.9% with a median of 0.1. These are all relative lifts. Yes, John, just like the original paper. So it is very common in A/B testing to focus on the relative lifts. When we tell you revenue improved by 2%, it's easy to compare it with another experiment. If we tell you revenue moved by 0.02 cents, it's not clear how that compares over what duration and things like that. So very, very common. Absolutely right. These are all relative. So how do we set the MD? We want to be realistic, be able to find sites that can actually detect this effect. So we went for a 2% MD. Remember, the original paper, 55, we're going with a minimum detectable effect that is much, much lower. So we need a lot more users, right? In fact, after the first two replications were not significant, we decided let's try to find another site which is bigger, where we can get the MD down to 0.5%. Okay, so let me now share with you some of the results. SeaWorld Orlando. This is actually a third replication and largest. So I'm starting with this one. You can see what they changed. Here's the square. Here's the round. Co-op in Norway, one of the largest company. I think they're the 15th largest company in Norway. They have two sites. One of them is OBS, which they sell groceries and PlayStations, gardening tools, a very sort of Amazon-ish like site. And again, you can see here, there's a buy and a pick up at the store, square, and these were rounded. And they have another site, which is a do-it-yourself chain, different price points, but basically the same UI. So these were the three replications that we tried to do. Here is the summary of our results. Okay, I'll leave this for a few seconds. You can see here the original BAC study, which is the only A/B test online, has about 500 people in each of the control and treatment. We have not just twice as large, which is what you recommend for replications. We made it 2,000 times as large. BAC also had a couple of smaller studies that were not online. They're done with students and other things. Again, you can see how tiny they are. But the effects were all massive, right? 55%, 46%, 108%. Look at our effects. 0.6, 0.16%, 0.29%, and 0.73%. None of these are stat sig in our replications. Okay, so remember, when it's not stat sig, you cannot say it's zero, right? You can only reject the null hypothesis. You can never accept the null, but you can say that, hey, if there is an effect, we had an MDE of 0.5% for this study, and it was below that MDE. Okay, I see a couple of questions. Let me answer them. The first study, given that it wasn't randomized because the author claimed causal impact by using diff and diff, they could if they ran a diff and diff analysis. They didn't, right? They gave it to Google to run for a few days and then based the results on the A versus the B. But Google was not randomizing. Google was intentionally trying to find out which ad is appropriate for which person. The results are invalid. Are these replications the same UI change at the same? Okay, so this is not a reproduction. I can't run the experiment at the startup that they ran at. That startup no longer exists. This is what's called a conceptual replication. We take the claim from the paper that rounded corners improve online click-through rate, and we implement it on 3 different sites. Okay, so that's a good comment. These are conceptual replications. They are not reproductions of the exact same study at the same website. Yes, so it could be that there's some sort of an effect or a moderator that would explain, but then it's the onus is on the authors to say, it's not rounded shapes, it's rounded shapes in these conditions, or that's what we're trying to figure out. So good comment. But now, given that we've run this on 3 different sites, and there's actually a 4th one that we did that's in the appendix if you want to look at it. We couldn't find a place where this works, right? And there's, again, huge evidence this is not going to work because this is what's called the winner's curse. These are too tiny. And you'll see the small telescope study in a minute. It's just now. So what's this small telescope methodology? It's a really cool idea. Remember, if they publish results that are barely significant, right? The key study, the A/B test, had a p-value of 0.037. So the confidence intervals are wide. So there's a good chance that any study is going to actually be in that confidence interval, right? They claim 55%. Had we gotten like a 2%, it seems crazy that we get 2% and they get 55%. But because they're so borderline, then the confidence intervals will encapsulate basically our result. So it's hard to sort of claim that we're going to try and dispute the result using confidence intervals. What we do is a beautiful idea by Simonson to say you can't ask whether results are consistent because they will be given the small p-values, but you can say, was it designed? Did it have sufficient power to even make the claim? Okay, and the idea, this is why it's called a small telescope, is that, look, there's some astronomer that says, hey, I found this planet. You can't say you didn't see it, right? But you can say is, look, we looked with a much larger telescope. There's nothing there. And given the size that we could see with a small telescope, your original telescope was too small. It could not have seen an object so tiny that we can't see in the larger telescope. Okay, so this is this beautiful graph of small telescope. Here is the initial study. You can see here the 55%. And this is the confidence interval. Notice that, it goes from like 140%. The mean is at 55, but it's very close to 0, right? So anybody that claims, it's much smaller is still going to be in the confidence interval. This is the other 2 studies in the paper. Again, this was, slightly below 50%, but very wide. And this is over 100%. And this confidence interval goes to 523%, right? So these are massive confidence intervals. Now, these are our results with confidence intervals. Okay, so you can see the tiny confidence intervals here, and this one's barely visible. Okay, now, what we are saying is, look, we got such a much larger telescope than you do, and we don't see it. And the methodology that Simonson suggests is, look, if their 33% power is, if they don't have 33% power, then you can say you have too small a telescope. And these are the 33% power lines. So if these power lines do not fall into the confidence intervals that today we show in the replication runs, then we can say, hey, you guys, your telescope was too small. Your study was just too small, and you suffer from the winner's curse. So At this point, we believe the original result was overstated by about 2 orders of magnitude. So, look at our three results. We get somewhere between, actually, the meta-analysis shows 0.2% relative to their 55, right? So, it's a lot smaller if it is even not zero, right? Remember, we cannot accept the null. We can only reject it. We got statistically insignificant results, meaning it's consistent with the zero given our sample size. It is possible that had we run with larger sample sizes, we would have found the difference. But right now, our best estimate of the difference is sort of the average of these three, right? We did a meta-analysis and it's 0.2 versus 55%. So, key point, power analysis is essential. They didn't do a power analysis, and therefore they ended up with this winner's curse problem. Okay, what about the other patterns, right? This result, clearly unusual, 55%. A lot of people think, oh, this is absurd. Let me actually answer Bogdan's question. I work in payment orchestration. We powered our experiment for an MDE of 4 percentage points based on external benchmarks. We see consistent 1% lift, but flat results for others since we failed to hit. Yeah, so it's a good question. So if you run an experiment and you power it for a certain amount, let's say an MDE of 4%, and you get only 1%, you have to understand that there's a lot of noise in that 1%. Could be plus 1%, could be minus 1%. So the confidence interval is going to be very wide. The right thing to do is to do another replication run and then combine the two, and then you'll have more power, right? This is what I would do in your situation. Now, if you don't have the time, if you don't have the thing, people do launch experiments just based on the hope that this is going to be more positive than negative, but the reliability of launching things that have low power way below the MDE is very, very low. And I have a whole paper on false positives in A/B tests. So what about other patterns, right? We showed you this sort of unreasonable claim, but there's other patterns out there. There's a performance claim, there's coupon codes, sticky call to action. So now we're going to describe to you seven large-scale experiments that are summarized in this paper. And the median replication for our 7 replication has 2.2 million users and 80% power to detect MDEs. And we associated with every pattern a small sort of MDE that we think is reasonable. Okay, now a few things to note. Even at our scale of 2.2 million users, we did not have power for many key business metrics. Right? A lot of people run experiments with 100,000 users or 1 million users. We ran with 2.2 million users as the median, and we did not have sufficient power to look at, say, revenue per user, right? Except for one experiment. So we had to resort to surrogates. So we looked at things like click-through rates, we looked at the carts, we looked at capped at the cart, which lowers the variance a lot. Those of you that know statistics, it's called Windsorizing. John says, have you tried Cupid? Indeed. Remember, we're using other platforms. Cupid is a variance reduction technique, and John is sort of laughing because I was a co-author on that paper. But because we're using vendor software and partners, some of them support Cupid, some of them don't. So if they support it, we use Cupid. If they don't support it, we don't. You'll see the next result uses actually Cupid, but the others don't. So our conclusion is, wow, even for these patterns that are out there for a while, and there's a lot of results, the effects are highly, highly exaggerated. Okay. Got a question here. Let me see how I'm doing on time. Let me post some of these questions and leave them to the Q&A. I'm happy to run over and answer the questions, but I want to finish a few more slides here for those that have to leave on time. So, the punchline, even for a lot of the things that are sort of focal, in the industry as, more substantiated, even those were highly exaggerated. 5 of the 7 replications that we're reporting here, we were not able to get statistically significant results at the standard alpha of 0.05. So here's the first one. That was success. Page load time. Talabat, food delivery service owned by Delivery Hero. They serve the Middle East. They ran the A/B test, which improved the performance of the homepage by caching. So they have a homepage. It was very slow. They cached the homepage. Most of the components of the homepage were cached. They still had a few components that they needed to sort of personalize, but it was a huge improvement to the performance. That said, it was only one page. So there are several results out there that say, hey, if you improve the performance for by 250 millisecond, sorry, by 100 millisecond for Bing, you get 0.6%. But it's Bing is essentially one page, right? Amazon has this experiment that is very famous, but it's all of Amazon pages. Here, they only changed the homepage, and the rest were not sped up. 2.2 million users. They gave us 80% power for an MDE of 0.5. Cupid was deployed to reduce that MDE. So we had lower actually detectable effects. And this is the result. We got 0.3% statistically significant improvement to revenue. So watch the key metrics here. Look at this. The homepage, time to interactive, which is the key measure of performance, was reduced by 58%. Right, on average, and the 95th was reduced by this 30%. The revenue per user was 0.36. We suspect it is slightly overstated because they used EPO, which stops the experiment in a dynamic fashion, which tends to exaggerate the results. So this may be slightly exaggerated, but not too bad. I would say it's probably 0.3. And then the other metric is also supporting this, the orders per user, another 0.3. Okay, so pretty interesting result, good ability to replicate this. And as I mentioned, this is only one page. Then we have the coupon code pattern. Okay, I mentioned Co-op before, the 15th largest company in Norway. They have two websites, the OBS and BYGG, and they have this coupon code, right? Those of you that know how to read this, but it means coupon code. And they removed this. Yeah, that was the experiment. The idea is that when people see the coupon code and they don't have one, they sometimes abandon. Disappointingly, the results again, not stat sig. We did get a positive lift, but again, with an MD of 2%, we cannot claim that this is statistically significant. Our p-values are pretty high. And the metric that we used is purchase 0.1. Notice again how limited we are. We could use the Boolean version. Did the user purchase at all? 0.1. But we couldn't do things that we really wanted, like revenue or orders, right? Or even purchases as not a Boolean. So they're well below the 2%. So we could not reject the null. Another pattern, sticky call to action. The idea is that you do something at the bottom and it's sticky. When the users scroll, they see it, right? The Talabat, again, which I described before, they added a sticky component. This was already there, so this was semi-sticky. So this is not a classic call to action, but they added this sort of a savings bar telling you, hey, how much are you saving? So that to encourage you to spend more. Large experiment, 8.1 million users. Look at this. Stat sig negative. Borderline, but still surprisingly stat sig negative. And then revenue per user, again, stat sig negative. This was the summary that the company wrote. Didn't achieve its objective, which was very interesting as it was previously viewed as a sure win, right? I talk about in my class about how humbling it is to run controlled experiments. Everybody thought this would win. And yet it wasn't even flat. It was slightly negative. Again, these are borderline. They could do a replication run, but it certainly doesn't look like it's very positive. There's another replication here. Ben says, why do you think it failed? I think it failed because the folklore out there is over-exaggerating the value of these patterns, right? People publish when it's successful. We don't see the ones that fail to replicate. So they had 3 treatments where they added these components. There was a buy button and price, or buy button price and a checkout, or something that initially initiates checkout. And we looked at conversions. Again, 0.1. We had an MD of 1.5%. And guess what? All these treatments, one was stat sig. Okay, now somebody just had mentioned before, ASR, whoever you are, you said adjusting for multiple comparisons. Now, notice we didn't run one experiment, we ran six. So when you get a statistically significant result, 1 out of 6, well, it's less trustworthy, right? And it's worse because the same treatment, T2, on the other side was negative, right? So that reduces the trust in this result. A meta-analysis said this does have a positive effect of 0.86 with a stat sig very borderline p-value, but given these results, we don't trust it. We think this is an example of the winner's curse, right? We are now rerunning T2 with a lower MDE with a client. Okay, so I'm showing you the messy reality is we had a win that, somebody could have launched this and said, look, this p-val's got 3 zeros in front of the 7. But given that this is just borderline on our MDE, and this was a negative on basically another similar site, that raises a question about whether this is just the winner's curse. We're running 6 experiments here. If each one is a 0.05, then yeah, there's almost a 30% chance that you'll get a stat sig by chance. So let me summarize and then go into the questions. So first of all, notice the limited power. These are relatively large sites, and we did not have sufficient power for key business metrics within practical time horizon. Some of these ran for 16 weeks. Some of them ran for a few weeks, which is my norm when I'm used to running at Bing and Airbnb. We were running things for 2 weeks. For a lot of these sites, power is a huge problem. And whenever you see an experiment that's got like 100,000 people, just realize there is no way that have sufficient power. It's very likely that experiment is unreliable. As a workaround, because we couldn't do the business metric, we used surrogates, and we added capping. Capping helps a lot. So if you look at something like revenue or orders, any sort of account metric, then you'll be surprised at how many people you have in the data that have massive numbers that are unexpected. So saying that anybody that has over X is going to be capped to X is a way to reduce the variance. You are taking some risk. You're introducing a bias. You're not including the big whales, but there's few of them. Obviously, prior effects were overstated, right? We thought we had relatively conservative MDEs, but obviously they shrunk a lot now. 8 out of our 10 replications were not stat sig. Only the performance one and this other one on the call to action, which is borderline. Now, this doesn't mean that there are no moderators. So it's possible that there are certain conditions under which the pattern will work. We just have to run a lot more experiments to identify whether there are good moderators. Right? For example, I do think that coupon code sites, there's a difference between a site that you visit every day and one that you visit infrequently. That could make a difference. Also, we only looked at conversion, and I think coupon codes have a larger impact when people are going to spend a lot of money. So my obligatory last slide here. If you want to learn more about A/B testing, I know I jumped here with using a lot of terms. I sort of teach them in more details in the classes. So I teach 2 classes on Maven, and I'll put the links in the chat if you want to look at them. There are 2 classes. The first one is one I recommend for most people, 5 sessions, 2.5 hours. If you use this link, you'll get a discount. And then there's the advanced one, which I truly recommend only if you took the first, or you've read the book, or have extensive A/B testing experience. Because the most common comment I get on the second class is, I wish I would have taken the intro class because it was a little advanced. If you want to participate in the Trustworthy A/B project, there is the link. We are continuing to do replications. So if you want, you'll get free consulting from 3 people, Lucas, Jacob, and myself, if you agree to share the results afterwards. We are right on time, so it's supposed to be 45 minutes. What I'm going to do right now, so if you have to leave, I will not be offended, of course, but what I'm going to do right now is I'm going to go through the Q&A through the chat that I have not answered due to time constraints, and we'll answer them, and then I'll stay if you have a few more questions so that we can deal with them. So let me go to the screen. Okay, so Benzarota. For software companies with relatively low traffic, not Bing level of magnitude, and covariance only reach around R equals 35%, 35, so Cupid cannot decrease variance above 15%. What do you recommend product leaders do to help push the company towards rigorous experimentation? Uh, Leadership will not accept the claim that nothing in the company is statistically reliable, especially for small startup. So I mean, it's a sort of a classical question. What do? You can use surrogate metrics that have lower variability, like a Boolean instead of a count. You can cap metrics to reduce the variance. You can run the experiment longer, and you can replicate experiments. Now, I will say, if you have, 10,000 users, I'm sorry, none of these are going to be sufficient, right? So you have to rely on just copy what Amazon and Netflix and others do, because their UIs, their mechanisms have been tested to help. Okay, Bogdan, I think we answered that question. And then another question. Oh, that we got already. You might also consider the risk negative downside launch. Yep, I agree. When adjusting for multiple comparisons, is there a corresponding adjustment that is typically done for confidence intervals, which are analogous to adjusted p-values? So the duality theorem says that, your confidence interval should, 95% confidence interval should touch zero if it is not stat sig, right? Cross zero. There are multiple adjustments that are available out there. You have to realize that sort of in the extreme, like Bonferroni, which assumes independent, is probably too strong of a correction because a lot of our metrics tend to be correlated, and so you need to correct less than Bonferroni. But I'm not there, as far as I know, there's sort of no good theory to tell you how to do the multiple comparison correction for multiple metrics that are correlated. I mean, you can do things, but Benjamin Hochberg is probably the one that most people use for family wise. Ben asks, why do you think it failed? Um, okay, remember, controlled experiments tell you the result. Now we're into hypothesis land about why it failed. I do think they take up more valuable real estate, like RSP says here. I do think that it causes people to maybe focus too much, or damn, maybe I'll wait until a few more days until I get another item so I can go over the limit. So these are all conjectures. I think we have to run a bunch of experiments to understand this. Elise says, how do you decide on the MDE? So I showed you this slide where this is what you need to do. You have to say, look, what are typical sizes, effect sizes, when people run similar experiments, right? And the usual solution is you go to these repositories, Good UI, Evido, Guess the Test. There are several repositories out there that you can find. You can search for your change, and they have a lot of patterns, and you'll be able to find similar things. I'll tell you the sort of my rule of thumb is never put an MD above 5%. It's just too unlikely in online experiments, right? If you're developing a vaccine, yes, they need 30 to 50% effectiveness improvement. But for online experiments, if it is, when I see people running with MDEs over 5%, it's like, no, unrealistic. It's a rare home run that should happen one in thousands of experiments. Don't go for that. But I think this is sort of the approach. I think, 2%, which we've used for some of these, is still high, but, sort of reasonable trade-off because we couldn't find larger sites. You have to know the current conversion ratio, given the sample size. Yep, the MDE. How do you pick the right surrogate? So there are papers out there that allow you to sort of establish some coverage of surrogates. But I think most of the time we pick surrogates based on our background information and some data. So, if you can't do revenue, then you're going to do conversion. Right now, conversion assumes that the order size is the same, average order value. If that's a realistic assumption for your experiment, then I'd say absolutely move to conversion. Right? You're making an assumption, but if it holds, then the surrogate metric is good. Now, at the cart, a little less comfortable, right? Because if you look at the correlation between at the carts and purchases, it's like 35%. So it's not as good a signal, but still, if you're testing button colors, yeah, you can look at clicks, right? Because, if they're clicking on the button, that's a good sign. Okay, let me see what else. Growing my networks. By capping, aren't we excluding the big whale? So first of all, we're not excluding, Flavio. I want to mention very explicitly, we are capping. We're deciding on some max, and we're saying if you're greater than the max, we'll count you as the max. Now, to give you some examples, and I'll give you the slide here. It's in the appendix. This is the at the cart distribution at one of the sites that we tested. So yeah, I can imagine that somebody over a period of a couple of months where the experiment ran, they added 60, 80, 100 items. I can't imagine people that add 5,000 at the carts, right? These guys, and these guys. So it's not that we're removing the whales. We are likely removing bots or some B2B agency, right? At Amazon, most people buy a few books, and then once in a while we would get like an order of 2,000 books. It's a library. At Airbnb, most people book a few nights. We had some people that book, 100 nights for the next 30 days. Well, you're not going to stay 100 nights. You're an agency, right? And so agencies are less likely to be impacted by the UI. And so I don't feel too bad saying, okay, we're going to clump the agencies and say, you book more than 50 nights, we'll count you as 50. You're still significant, important, but we're not going to allow the variance to grow because remember the difference between this item and the mean squared goes into the variance formula. So when you have a skewed distribution, those outliers kill your, increase your variance and then kill your ability to get statistically significant results. It's a trade-off. I normally recommend that what people do is they keep the original metric and add a couple of capped metrics. So you can say, for this metric, I'm going to cap it at 100 and at 1,000. And then if the metrics all point the same direction, you're fine. If the metrics, some of them are stat sig and some of them are not, then it warrants a deeper look and saying, okay, if the cap metric is stat sig, maybe I need to run it longer because it's an early indicator that something is happening here. So great question. I think we answered this one. Never mind. Firebase has an A/B testing tool. So again, you have to be careful with these tools to see if they completely randomize or not. I have not worked with Firebase, so I cannot give you the answer here. Can we set up OEC as something like conversion rate for trial purposes and use historical estimate for trial to paid? You can. Again, it's a surrogate. If you're convinced that the trial to buy is stable, then you're okay. I would build that as a guardrail. Right. So yes, you might get more power by looking at the conversion rate, but you want to make sure that you're not changing it. I actually have a beautiful example of that in my class where this failed in some experiments that we did. So good question. And it's important to realize that when you're making an assumption, try to test them, build that as a guardrail. Say, I want to make sure that the trial to buy did not change statistically significantly. If you were to open a startup right now, would you not? Yes, I would definitely start off if before you have 100,000 users that you can put into the experiment. I would use best practices, industry best practices. You also have to realize that when you're a startup, you may be going for home runs. So if you're making big changes that you think might have the potential for a 20% lift, yes, you might want to run them, but be really careful. Be really careful. Greg says, so capping is trimming the outliers. Yes, Windsorizing, capping, trimming, these are all the same term. You're not deleting it, you're capping it. You're saying anything greater than X is X. Do we need to power just for the main metrics or even at least one metric? You need to decide on your power. Normally, what people do is they power for the OEC, the overall evaluation criterion, and then they do what's called the reverse power calculation to see what power they have for the other metrics, for the guardrails. And if you're not happy with those, then you may say, okay, I need to increase the power so that I can protect my guardrail. Good questions. Okay, we are out of questions, which is great. I'm happy that we were able to get through the questions, and we are going to. I'll just maybe show you the 4 slides I have in the appendix. If you want to look at them, you'll get the deck. So we talk about capping here, and we show this distribution. We show what it does to your sample size requirement. So look at this. Uncapped, I need 13 million users. If I'm willing to cap at 10, I only need 2 million users, 2.5 million. So there's a factor of 8, right? If I want to run an experiment for 4 weeks, I can run it capped at 10. I can't run it uncapped because it would now, instead of 4 weeks, be 32 weeks, right? This is what the difference it makes, right? So typically in a scenario like this, I would recommend run the most extreme capping, which is the one Boolean, did they change or not? And then something like a 10, which seems like a good trade-off. And the knee here, did they do 10 at the carts? And keep the original one. I mean, maybe there will be a big difference, but it's most likely going to be such high variance, I will not get a good signal out of that. This is the replication that we did on another round of square buttons. It was sort of the largest experiment. Again, you can see here the square versus the round, 7.4 million users. The OEC was pre-declared as at the cart rate. We had 80% power, and again, for at the cart, we had 2.7%. If we cap it, look at this, we now have a more realistic MD of 1.2%. And these were the results. Interestingly, not only was this not 55%, it was slightly negative. It's basically a 0. On these metrics, it was slightly positive, but look at the p-values. So nothing here is stat sig. That is it. Last question I got from Flavio. In your book, OEC differs from the experiment success metric, making some of the slide example a little unclear for me. Could you elaborate on the differences? So we think of a family of metrics. There are success metrics, there are driver metrics, there are guardrail metrics, and then there's like debug metrics. The success metrics are metrics that the organizations may have, but they may not be sensitive enough for an experiment. Like some people can say, Walmart, for example, for many years had a success metric related to market cap, right? So you can't run an experiment and look at the stock price. That makes no sense. It's not sensitive enough. So even though it is your success metric, it's not going to be part of an OEC for an experiment. So the OEC has additional constraints. It has to have more sensitivity and the belief that we can move it in a short run experiment. Okay, folks, thank you so much. We will end here. And again, you'll get the slides. You'll see the posting if you want to look at it. Thank you, everyone. Have a great day.
Thank you very much.